So we're going to go through each method of solving a system one day at a time. So when we have a system, remember that a system is two equations that contain the same variables. Solutions and methods. So there's three of each. So the types of solutions are one solution graphs. When they're graphed, one solution, the two lines perfectly intersect at one coordinate point. Could be there, could be anywhere, they just cross once. There is a no solution graph. No solution. The two lines are perfectly parallel, and they will never cross. The last one goes by a few different names. Infinitely many, also known as an all solution. That's what I learned it as, infinitely many. We have one line, and then our second equation happens to land right on top of the old one perfectly, so that every coordinate point that these two share happens to be a solution. So that's a solution, that's a solution, that's a solution, anywhere on this graph. Three methods: graphing, substitution, and elimination. This is what we're going to focus on, one method for the next couple of days. All three methods can be used at any time. I'm going to prove that by doing one tough graphing one that you shouldn't graph, but I'm going to graph it. I'm going to take a substitution problem that probably should be an elimination problem. And then elimination, this one's kind of the catch-all. It's, other than making crazy fractions and decimals, can't make elimination too crazy without multiplying to super large numbers, but we'll have one of those later on as well. So to start off with graphing, what we want to look for are y equals equations. If they're in y equals equations, they're easier to graph, and we can get a solution hopefully better. Some of the pitfalls, though, of graphing is if they're not in graphing form, or if they don't intersect perfectly. So if they don't intersect perfectly, we have to estimate, and if we're looking for extreme accuracy, estimation is not what we want. So just to follow up from our last graphing unit, we have our first graph here. We start at -2. Rise 3, run 1, rise 3, run 1. So I'm hoping one of these dots right here is our solution. I'm not 100% sure, so I'm going to draw my line in there. I want this line to be blue. There we go. Second equation, we start at 4. 1, 2, 3, 4. We drop 3, run 1. Perfect. Drop 3, run 1. Drop 3, run 1. Just because we know where the solution is doesn't mean that we get to stop early on the problem. Last thing before we can say the problem is done, we have to record where these two dots, or this dot is, where these two lines cross. It is at 1, 1. Graph another one. Again, both in y equals form, so that is helpful. Start with our first one. Down 3. The negative only goes with one of the numbers, so we go down 1, right 2, down 1, right 2, down 1, right 2. Up 1, left 2, up 1, left 2, up 1, left 2. So hopefully one of these dots is where we find our graph. Our next one, we start up 3. 1 over 1 slope. I see where our two lines cross, but before we do that, we should draw. We need to draw on our lines. Then the last thing, record where they cross. This one's -4, -1. If we don't have graphing form equations, honestly, we should probably use a different technique. Graphing should not be our go-to. But since that's what we're going to do, we're going to convert both of these into y equals equations and graph from there. This first one, we have to move the 2x to the other side. That leaves us a -y equals -2x plus 4. Divide by a negative, and we get our y equals equation 2x minus 4. Did do a lot of work down here for that one. Second equation, we have to subtract x. This gives us 3y equals -x plus 9. Everybody has to be divided by this 3. We get -1/3 x plus 3 as our equation. Since I'm already using red, I'm going to graph the second equation first. So we start up 3, down 1, right 3, down 1, right 3, up 1, left 3, up 1, left 3. There's our line. Next one starts down 4, up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. Could also go down. There's our intersection point. Let's record where it is. Yeah, let's use that choice. It is at 3, 2. Now for this last one, this should definitely be a different equation. But we're going to graph it and we're going to see what happens. So I still want to get it into y equals for both of them. So let's start with the top one. I would subtract 7x, so that leaves me -8y equals -7x minus 12. I divide everybody by a -8, and I get 7/8 x plus 12 over 8. 12 over 8 can be simplified. 4 goes into both of them. 3/2. Alright. So we have 7/8 x plus 3/2. For our next one, we subtract the 2x. That leaves us -6y equals -2x minus 22. I divide by a -6 on both sides, and that gives me 2/6x plus 22/6. The negatives cancel each other out, similar to what happened up here. Simplifying that, I get 1/3 x plus 2 goes into both of these, 11/3. These are both able to be graphed, though not easily, so this one starts up at 3/2, so that's 1.5 right here. And then goes 7/8, so it's almost up 1, so just short of a half. So I can't count, like I don't have a graph big enough, I can't go up 7 over 8. If I had a bigger graph, I could probably go up 7 over 8. I'm going to have to do the simplified version of this. So 7/8 as a decimal is, I believe, 0.875. And so we put that over 1. So we go up 8.75 over 1. So right about there. Our next graph. So let's draw on our line for that one. Next graph. It starts at 11/3. So that's 3 2/3. So 1, 2, 3 2/3, right about there. We can go up 1 over 3. So it looks like these two lines basically cross right there. But unless we've done everything 100% perfectly, we can't be sure that is supposed to be the right answer. We just have to estimate whatever we think it is. 1, 2, 3. 1, 2, 3, 4, 5. But it would be less than that. It's not a perfect whole number. So it's still 3. I just got caught up with the 5 because I kept counting. 1, 2, 3, 4, 4.6 maybe? If we were to use a different method to solve, we'd find that this one actually has a perfect whole number solution.